because we want to stay on track with the course. All right, so, and some of it is review, so it's okay. So this is chapter 13. It's a continuation of chapter 12. It's on probability, and it just expands on what we've already learned. So we will get the general addition rule. We cover independence and the multiplication rule. We also discuss in this chapter conditional probability. There's also the general multiplication rule and showing events are independent. Now the tree diagrams we will not be doing here, but some students in the past have told me they really like the trees and they've learned it before, and that's how they like to set it up for finding probabilities. However way you figure out your probabilities, if you like the trees diagrams, you can use them. We're not going to be covering them or testing them, but or the Bayes rule. We won't be covering that this term as well. Okay, so we will take those off from the course. It's listed in the schedule as well. But all the rest we will cover. And we also here, this is a review for the midterm too. The probability rules, we have 4. Rule number 1. So for any event A, the probability must be between 0 and 1. If it's equal to 0, it means the event will not happen at all. And if it's equal to 1, then it means the event absolutely will happen, right? And everything in between. So if you have a probability that's more than 1 or less than 0, it's not a probability. Okay, it has to be between 0 and 1. Rule number 2, we define S, capital S is the sample space. And so the probability, that is our notation, that capital P, right here, capital P, is probabilities of the sample space, all of the possible events is equal to 1. They must sum to 1 in order to be a valid probability model. Rule number 3, the addition rule, we covered this as well for disjoint events, right? If A and B are disjoint events, then the probability of A or B is the sum of those probabilities. That means they can't happen at the same time. So we use the example of buying a car. You've got it narrowed down. You're either going to buy car A or you're going to buy car B. You're not buying them both. So there's no A and B. The intersection would be 0. The probability would be 0 for that. Okay, and rule number 4, for any event A, we can call this the complement rule. The probability that A will not occur is going to be equal to 1 minus the probability that A will occur. Okay. That's chapter 12. Here's some Venn diagrams. These are helpful, very helpful, especially when you get into being given information, depending on what you're given. We call them John Venn or Venn diagrams. And there is the one on the bottom left. That is disjoint events. So you can see visibly here, like just by the picture, we can see that they have nothing in common. There's no overlap. So the probability of A and B, you can see, would be 0. There's just nothing there. But if they are not disjoint, then A and B is not disjoint, then it consists of common outcomes. And then we have, that takes us to our addition rule. Okay. So here they are right here. So if they are disjoint, that's everything on the left, then that's the probability of A or B, which is the sum probability of A plus the probability of B. But if the events A and B are not disjoint, then you have what's on the right. It would be the probability of A or B is going to be the probability of A plus the probability of B, right? We're taking all of A and we're taking all of B and adding those probabilities, but we need to subtract the overlap, that intersection, because it will be counted twice if we don't. So we take all of A, just imagine taking all of A, the probability of A, and then B, the probability of B, and then we have to subtract the overlap, which is the probability of A and B. So that's the addition rule. If they're not disjoint, if they are disjoint, then it's just simply that, because it would be the probability of A or B if they're disjoint would be the probability of A plus the probability of B, subtract the probability of A and B, which is just 0. So you would be subtracting 0, right? But if they're not disjoint, then you need to subtract the probability of A and B, which will be something that is non-zero. It'll actually have a number between 0 and 1. Okay, so we won't do the examples at the end of this chapter right today, but we will do the ones during the chapter. So we can try to do this one. Let me see. So we have print books continue to be much more popular than books in digital format. So we have a 2019 survey found that 65% of adults had read a print book, B, in the preceding 12 months. 25% had read a book in digital format, D, they call that event D, and 18% had read both a print book and a book in digital format. So if we randomly select an adult at random from this population, what is the probability of B or D? Right, so what I do is I draw them starting with the intersection. So if it's both is 18%. So I do this in proportions because the math works better if you just leave them in proportions instead of percents. So 0.18 is the intersection. And then B, if we say this is B over here and this is D over here, what's left out of B would be 0.47, because 0.47 and 0.18, we should get 0.65, right? That's what's given. So what would be the piece that is D? So we've already got 0.18, but all of D together adds up to 25%. So what should I put in for the part that's missing? What's missing? You know what? Yeah. Yeah. So it's going to be 7%, so 0.07, right? 0.07, is that correct? 0.07, I think. So, right? 0.07 plus 0.18 comes to 0.25, right? Because the probability of B is equal to 0.65, and the probability of D is equal to 0.25. And when you add them up, so we always start from the intersection and work our way out, and then we have all the pieces. And then we want the probability of B or D, which equals the probability of B plus the probability of D. And we need to subtract the intersection because, that's B, because we don't want to count them twice, which equals 0.65 plus 0.25, subtract 0.18, which gives us, you can work that out, 0.65 plus 0.25, subtract 0.18. The probability of B or D. So this is in words, the probability of, so we randomly select an adult from the population, the probability that they have read a print book or a digital book is what? What's the probability? Yes. Pardon? 90? Yeah, print or digital. So that's what B is. Print or digital is going to be this. So it's going to be the probability of B plus D. And they're not disjoint events because they could have read both. So you can tell this is not disjoint because they could do both. If they had read both, it would be 0.18. So we have to subtract that out because we would be counting it twice. So this ends up being, anybody? What's the problem? Yeah. Yes, good, 0.72 or 72%. Right, you can put it that way too. And so that is how we calculate it. What if we wanted to know neither B nor D? What's the probability that they've read neither a book or a print book or a digital book? Neither. Yes.
1, 5 plus 5 plus 0.18 is both kind of fit into the journal.
Okay, so the probability that it's B or D, you're close. It would be right. Right, but you would want to just say, so you want to go, the probability of being a print or a digital is going to be, so neither would be just 1 minus the print or the digital. It's just going to be 1 subtract 0.72, 0.28. Okay, it would just be neither. It's neither either one of those. Because neither, if you want, I can expand this out more to have this. This is the whole sample space. So if it's neither, it's all the stuff that's outside. Remember the full sample, this is the sample space. All of it should add up to 1. So all of that outside bit is 0.28. So if so you can look at the picture, it's going to be everything outside B and D. So the probability of being outside the books, so the probability of reading print book or the probability of reading a digital book, everything outside of that is going to be 0.28. So the probability of neither B nor D is going to be 1 subtract 0.72, which is 0.28. Does that help? The picture helps because you can see it has to be everything outside. And it has to sum, the sample space, the entire sample space has to sum to 1. So if you add them all up, you have outside is like where I've drawn in, where the lines are out here. This part here all has to add up to 28.28. And if you add all those pieces, so 0.47 plus 0.18 plus 0.07 plus 0.28, the whole thing adds up to 1, and it does. And then we know it's a valid sample space. So yeah, the picture helps too, to see it. Okay. Independence and multiplication rules. So if we have two events, A and B, and they do not influence each other, so knowledge of one does not tell us anything about the other, or the probability about the other in particular, then these events are said to be independent. Okay, so we talked a little bit about this last time. You could have two independent events, such as, you know, a family having a boy and then another boy, and then the next one, not necessarily a girl because they had two boys. It's still an independent event. It could be either or. So it doesn't depend on what happened in the past to what will happen in the future. So it's independent. Nothing is influenced from the past. So if they are independent, if events A and B are independent, if knowing that one occurs does not change the probability we assign to the other occurring, then we multiply. So the probability of A and B, that has an and there, and they're independent, you need both, and independent, then we multiply them. So that's independent and the word and go together. Okay. We'll come back to that. Conditional probability. So conditional probability is if we do know a little bit about the other event. So let's suppose we have, well, it says here the probability we assign to an event can change if we know that some other event has occurred. It's more some information, and it could increase the probability or decrease the probability. So this idea is the key to many applications of probability. When we are trying to find the probability that one event will happen, given, we use the word given, and it's got this little notation here, a pipe. It's called a pipe. It's on your keyboards. It's a pipe that we use. So the probability of B given A, so that means the probability, what's the probability that B will occur given A has occurred? So that can change the outcome here, right? If they're not independent. So what's the probability it's going to continue raining today, given it's really dark clouds in the sky, right? If you know some more information about it, it can change the probability. It can help answer the probability question too. So if we, given the information that the other event is already known to have occurred, we are trying to determine a conditional probability. So the probability of A has to be greater than 0 because we don't divide by 0. So it has, the probability of A has to be greater than 0 itself. Then the conditional probability of B given A is written like this. So our notation is the probability of B given A is the probability of A and B occurring together at the same time, but we divide out the probability that's been given. So the probability it will rain today, given that we have clouds in the sky, dark clouds in the sky, we do the probability of rain and dark clouds, but we want to divide out the probability of the dark clouds because we know that is occurring. So everything past the given means that event has occurred or will has yeah, it's already known to have occurred. Right? So you just have to remember B given A is A and B, the probability of A and B, and then divide out that information we know. So it's just information we know that has occurred. So let me just highlight it's given the information that the other event is already known to have occurred. What's the probability that the patient has lung cancer given they smoked 40 years? It changes the probability space, right? The space states changes, and so does this. If we have additional information, if it's just a random person, what's the probability of a random person having lung cancer? It's going to be, different than if we know that they smoked for 40 years or not. It changes. Okay, so that is conditional probability, and we will see more examples as we go. Yeah, here's one here. So this is, remember the Benford's law, that table? We did that in chapter 12. The table where the probability that you randomly select a number from a page or list of naturally occurring numbers, meaning it's not like, 1, 2, 3, 4, 5. It's just naturally occurring, like the populations of cities in the large cities in the world, or we could look at the areas of lakes or the volumes and so forth. So anything that is naturally occurring. And we know that if the probability that that number starts with a 1 is going to be higher than 2, and it will be higher than 3, and you can see the probabilities decrease. So that's Benford's law. It expands on that idea, and it does a conditional probability. So let's suppose a corporate budget amount has been randomly selected, right? So we want to know what the first digit is. So if A is the event that the first digit is at least a 2, and B is the event that the first digit is no more than 5, what is the probability of B given A? Well, we write it out. Make sure you write it out, because sometimes we forget to divide. We want to remember, always remember to divide out what's been given. That's the formula. And so what we want to do, well, what's the probability of A? The probability of A is going to be at least a 2. So that's going to be 2, 3, 4, 5, 6, 7, 8, or 9. That's the probability of A. We'll make it all that color. And then let's do like green maybe for the probability of B. B is no more than 5. So the event, and I notice a T, that should see event. The event that it's no more than 5. Let me grab orange, that might work better. No more than 5. So that means it could be 1, 2, 3, 4, and no more than 5. So what's the overlap? What's the probability of A and B? Well, I have a yellow and an orange on 2, 3, 4, and 5. So that's the probability of A and B. So let's write that down. So that's going to be the probability of a 2 plus a probability of 3 plus the probability of a 4 plus the probability of a 5, right? And the probability of A, well, the probability of A is basically everything in yellow, right? It could be a 2, it could be a 3, it could be a 4, 5, 6, 7, 8, or 9. So the quickest way to get that probability would be to add those up, or I could do something else to get the probability of A. Right, the probability of A is at least a 2. So I could do 1, subtract the probability that it's 1, right? So the probability of A can be equal to 1, subtract the probability of 1. right? Because that would be, because the probability of A, you agree, is at least a 2. So it would be a 2, 3, 4, 5, 6, 7. It would be all those probabilities. I could add all those probabilities up, or I could just go 1, subtract the probability of 1. And I get it that way. So that would be 1 subtract 0.301, which is going to be 0.699. So that's going to be 1 subtract the probability of not A. So we're going to add these all up. This is going to be, make sure I've got lots of room here. So this is going to be the probability of 2 plus the probability of 3 plus the probability of 4 plus the probability of 5. And then I'm going to divide by 1 minus the probability of not A. That's going to be 1. So that's going to be, we already did it above there at the top of the page, 0.699. And that's going to be the probability of B given A. So what's the probability of it being no more than 5, given we know it's at least a 2? It's going to be equal to this. So that's going to equal 0.682 or 68.2%. So in words, what's the probability that the first digit is no more than 5? Given we know it's at least a 2, like somehow, some way, you just have that extra information. You know it's at least a 2. So in other words, at least a 2 is, it's not a 1. So it's at least a 2. So at least, that word at least means 2, 3, 4, 5, 6, right? So you would go 1, subtract the probability that it's 1, and you get 0.699, right? Is everyone okay with at least? You may see something like that on the midterm too, at least. So if something is at least, in this case, a 2, then that means it could be a 2, it could be a 3, it could be a 4, it could be a 5, right? At least. Yep. Bayes? This isn't Bayes. This is Benford.
Oh, then
It could be, right? Because it was covered in chapter 12.
it's not given.
No, not the given. Not the given. But it could be like, what's the probability of at least a 2? Because we know how to do that. We can do the complement rule and go 1 minus the probability it's 1. We could do that part. The probability of A we could do. This here, this part here though, it's called the conditional. It's on the final in December. Okay. Those sort of questions. So yeah, keep it for the final. Okay. So if you were to do, like, let's say, what's the probability of B? The probability of B is no more than 5. So what's the probability of B? Yeah,
1 minus 679. What is add 1 to 5? It's still the
yeah, it's the effort's almost the same. Exactly. So the probability of B is going to be the probability of it being a 1, the probability plus the probability of it being a 2, plus the probability of it being a 3, plus the probability of it being a 4, plus the probability of it being a 5. And that would be your B, your probability of it being no more than 5. Okay, so that's the conditional. So the definition of conditional probability reminds us that in principle, all probabilities, including conditional probabilities, can be found from the assignment of probabilities to events that describe random phenomena. Now it's saying here, more often, however, conditional probabilities are part of the information given to us in a probability model. The definition of conditional probability then turns into a rule for finding the probability that both of 2 events occur. Yes. Yeah? So the overlap is what I have written in the, or,
plus B proposed one as the next to add five again.
but A and B is just the overlap.
Or plus. That's one.
Ye-
And
Oh, yeah, you could, sure, that would be valid, yep. Yeah. For sure. Any other questions? That's a good point. So that is talking about the general multiplication rule, which is right here. So the probability of A and B, this is basically the same as the conditional, but with some algebra. So if I do up here, if I do right here, the probability of B given A, we know that that's equal to the probability of A and B. And we divide out what's been given, so this time it's A. If I rearrange using algebra, if I rearrange this, then I can get what's down here. Right? If I just take the probability of A and move it to the left, I get this stuff, and then I have the probability of A and B on it on the left, and this on the right. Can you see how if you rearrange that conditional formula, we just rearrange it, we get this formula. So it's basically the same thing, but just rearranged. And then you have the multiplication rule. So if you know the conditional rule formula, you can easily then just using algebra, just rearrange it so that A and B are on one side and all the rest is over here on the right. You have the multiplication rule. So this is depending on what you know, what's been given, and which formula to use. So here, B given A, that's that pipe. So B given A is the conditional probability that B occurs given the information that A occurs, that we know A has occurred or exists, or, okay. So let's say, here's an example already done for us. So let's say we have Pew Internet and Technology Project. Company finds that 91% of Gen Xers use the internet and 89% of online Gen Xers say the internet is a good thing for them personally. What percent of Gen Xers are online and say the internet is a good thing for them personally? Right, so the probability of online has been given at 0.91 or 91%. And the probability of internet is good for them personally, given they're online, they're an online user, then that's 0.89. Right? Because why is it conditional? Because we know that it's that proportion of people. Right? And 89% of online. So of that subgroup of online Gen Xers, that's why it's conditional, because it's like a subgroup. We already know that they're online, and then we make it conditional. And then the probability of online and internet is good for them personally is just going to multiply those two values, 0.91 times 0.89, because the formula tells us, yeah.
one plus. Oh.
Exactly. Yeah, it'll be in there. Yep. It'll be given in the question. Yep. Good. Showing events are independent. So the conditional probability of B given A is generally not equal to the unconditional probability of B. If knowing that A, so basically what's the probability? So it's sort of like this. If they're independent, then it doesn't matter that B occurred. So this is sort of like, what's the probability of B being a boy, given A, you already have a girl? It doesn't matter. So basically, it's still just going to be, if they are independent, then it's going to be the probability of B given A, let's say a boy, given you already have a girl, it's just going to be the probability of a boy because it doesn't matter what happened in the past. Right? It doesn't, the conditional probability has no weight. So it's sort of like saying, what's the probability of having a boy given the family already has a girl? It's just going to be the probability of a boy. It's just going to default to boy. Right? Yeah. So if they are independent, then we have just this. Same thing if you have the probability of A given B and they're independent, then what will the answer be? If A and B are independent and it's this time A given B, what's the answer? Just the probability of A. Yes. Exactly.